About 20 more seconds to turn in homework, if you haven't already. Bring it on up to the front, please. Now about 10 more seconds. That's time. One brief announcement, that is that we will be doing lab number 8 next week. So I know there's been some changes to the schedule as far as lab goes. I will give you an updated schedule for the rest of the semester, including for discussions, including for lectures as well, probably over the weekend or by Monday. And that'll be either be in Canvas or I'll probably just print it out and bring it Monday as well. Good news is we're still on track for you to learn everything that you need to learn this semester, so that's exciting. But otherwise, we will continue with Chapter 7. Are there any questions before we get started? If not, then let's see, where were we? Oh, I believe we left off on the slide before this. Is that correct? We did a calculation. We did the ladder diagram of energy levels. You'll see that there's a ladder diagram of sorts in lab number 7. It's one of the questions. I will tell you, to do that ladder diagram, you only use the wavelengths that you calculated from lab. You don't use any of the other equations that we used. And if you have any questions about how to do that, please let me know. Okay? For that one, you're always looking at the difference between two energy levels. That's what those wavelengths were, remember. In lab, we said that for the red wavelength, that was the transition from 3 to 2. So if you use the red wavelength that you calculated, translate that into energy, translate that energy into kilojoules per mole, that is the kilojoules per mole between those n equals 3 and n equals 2 for hydrogen. Anyway, I think I'm sticking myself here. Okay, so where were we? We were about to talk about the wave-like nature of matter. When I say that, and we'll see that all matter does have a wave-like nature, but only for electrons. Only for electrons, or only for an electron, is the wave-like nature of matter significant. Okay, and so what that means is that if you have an electron source and you do what's called the double slit experiment, an interference pattern is observed that is evidence of the wave-like nature of the electron. And we said that when a single electron goes through these two slits, that is true, that the probability fields, 50% of the probability goes through each slit, and it is the probability fields that are interacting. Now, I don't know if you saw this today, but this is exciting. Google has just come out with what they are saying is a leap forward in quantum computing. Check it out. I don't know the details of it either. I just saw the New York Times article this morning. But the idea is that whereas most computers can only deal in 0 and 1s, the quantum computer can deal in probabilities and have more options involved there. It's super interesting. I don't know what the details are yet, but what we're starting to see, and this is super interesting, is actual effects, actual equipment using quantum effects. Which, sure, GPS systems already use it. They correct for quantum effects when they use it, but it's so, like, these are such tiny pieces of matter. Anyway, it's exciting for it to matter. Pun intended, I guess. Anyway, but if I say put a proton through this experiment, we would not observe an interference pattern because it's too big. And we'll do some calculations around that now. On the next slide, I want to give you what's called the de Broglie wavelength of matter equation. It looks like this. The wavelength of any type of matter is equal to h, which is Planck's constant, over m times v, where m is mass and v is velocity. Planck's constant, we gave it to you last time. It is given on your exam, 6.626 times 10 to the negative 34th. Joules times seconds. M mass. Whenever you deal with joules and mass, that mass has to be in kilograms. A joule is a kilogram meter squared per second squared. This is v and not frequency. This is v for velocity, lowercase v, and that's going to be in meters per second. Now, if this were a physics class, or sometimes in other chemistry classes potentially, m times v is called the momentum. It's your mass times your velocity, so it's really how much momentum you have. I don't know, I can't think of a better word. And the abbreviation for momentum is lowercase p. So another version of this equation you might see, and you won't see it, I don't think, in this class, is right there. Anyway, just, so I'll put parentheses around that. You won't see that in this class, but you may see it in other places. Now we'll use this to do a calculation. What is the wavelength of an electron traveling at 2.2 times 10 to the 6 meters per second? That velocity of the electron would have to be given to you. The mass of the electron does not have to be given to you separately because it's already given on your conversion and equation sheet. So you do have it. You just have to sometimes go find it. So now I've got wavelength of an electron. And if you remember from previous times, we do have an equation for the wavelength of electromagnetic radiation. That's different. There are two types of wavelength equations. It's going to be h divided by m times v. Filling in the numbers for Planck's constant, the mass of an electron, and the velocity. And you can actually go in and show that meters are the units you get out for your wavelength. You can see one of my meters here. Remember, a joule is a kilogram meter squared per second squared. We've got 2 of the seconds canceling in the kilograms too. Anyway, the answer is in meters. That's what I'm trying to say. And if you calculate it out, you get 3.3 times 10 to the minus 10 meters. And if we change that into nanometers, 0.3 nanometers. And we won't talk about the sizes of atoms until next chapter, chapter 8. But what we will need to know for now is this wavelength is approximately the size of the atom. Approximately the size of the atom. And that's why it will be important for atoms, because it's approximately that size. Any questions about this calculation? All matter has wave-like properties. What is my wavelength as I walk across the room at a velocity of 1 meter per second? Same equation, except this is the wavelength of Bill. Filling everything in, well, I'm saying about 79.5 kilograms. And that is what my driver's license says. And when you solve for the wavelength, my wavelength, I get 8.3 times 10 to the minus 36 meters. And it's true, it assumes that I'm one piece of matter, not made up of other pieces of matter, which is not a good assumption, but that's what we get. Bodie? How come the answer's in meters? Would you like me to prove it?
Yeah. No, I just wanted to know
all right. A joule is a kilogram meter squared per second squared. Right? And that's the definition of what a joule is, actually. But if you use this equation and think about kinetic energy being in joules, this is going to be kilograms, this is going to be meters squared per second squared. Like, that's what I always think of when I think of units of joules. And now, if this is a kilogram meter per second squared, the kilograms cancel. I get 2 of the seconds. Well, per second squared, that cancels with that one of those. And then since this is in the denominator of the denominator, it's in the numerator. So your seconds cancel, and you're left with only 1 meter left. Good. Completely unimportant, completely unobservable. If we were to do the same calculation for not me, but a proton, it would still be much smaller. A proton, if you remember, is approximately 1,800 times more massive. And so therefore, anyway, so it matters, this wavelength matters for electrons, it doesn't matter for other matter. And if it would only stop there, the world would be crazy enough. When you try to observe the wave nature of the electron, you cannot observe its particle nature and vice versa. The wave nature, and this is specifically for the electron, is equal to, I don't know if equal is the right word here, but is wave nature is represented by the interference pattern. And the wavelength that we can calculate. The particle nature is represented by position. Or mass. And what I mean by that is particles tend to have mass. Those masses tend to have positions. I've put in wavelength up here, but the wavelength is related to the velocity. So another representative of the wave nature is velocity as well. The wave and particle nature of the electron are complementary properties. What that means is that as you know more about the wave nature of an electron, you know less about the particle nature. As you know more about the wave nature of an electron, you must know less about the particle nature. And this is represented by an equation and a principle. That principle is called the HeisenbergUncertainty Principle, which says that the product of the uncertainties in both the position and speed, we've talked about the relationship between speed and velocity, of a particle was inversely proportional to its mass. There's an equation for this. It says the following: delta x, in parentheses, times mass times delta v is greater than or equal to h over 4 pi. Now, x is going to be position, but delta x is uncertainty in position. V is velocity, delta V is going to be uncertainty in velocity. M is mass in kilograms, H is Planck's constant, and pi is pi. And what this equation means is that the more you know about, or let's say, the less uncertainty there is in the position, since they're multiplied, which means they're inversely proportional, the more uncertainty you have in the velocity. And there's a limit to this. And this is a pretty small limit. Planck's constant, 6.626 times 10 to the minus 34th joule seconds. This is another one of those things that only matters for electrons. And when I say only important for electrons, what I mean is in Chem 400, if this were a physics class, I'm sure there are other particles for which this is important as well. But since we're using the Chem 400 basis, it's only important for electrons for us. However, this is also true of all matter. It's just unobservable for anything other than electrons. Any questions about this? Let me say one other thing. To find the minimum uncertainty, put an equal sign here. Put an equal sign. Alicia?
I've heard that before, and I was gonna ask why, but I'm afraid the answer probably is too complicated.
Actually, I can provide a little bit of information about why. Is your question, why does the Heisenberg uncertainty principle exist? I think I can provide a little bit of, shed a little bit of light on that. Electrons are so tiny that basically in order for you to put some wavelength of light or some, to basically when you probe them, you disturb them. And when you disturb them, you create uncertainty. So again, it's basically related to how small an electron is. And that if you're trying to figure out the wavelength, then you probe it, you either have to find out you have to disturb it in some way. So I think that's basically as much as I know, certainly for Chem 400 stuff. But the other thing you have to know, and that I know, is that this uncertainty is truly a limit. You cannot know both of these properties any better than this. It is physics. Okay? So it is physics, it is chemistry. And what I'd like to do is do a calculation with this. And for the same electron we had last time, we have, and traveling at 2.2 times 10 to the 6 meters per second, there's an uncertainty of 2 times 10 to the 5th meters per second. Which, if 2 times 10 to the 5th meters per second is a little less than 10% of this number, so it's about 10%. And if you wanted to find exactly 10%, you take this times 0.1, it'd be 2.2 times 10 to the 5th. I think one of the homework questions says, assume the uncertainty is 10% of the velocity. You guys know how to do 10% of a number. It's just a new application. What is the minimum uncertainty in its position? Well, we just said, replace this with an equal sign to find the minimum uncertainty. And then, let's see, we're looking for minimum uncertainty in position, that's delta x. We know the mass of an electron, we know its uncertainty in velocity, we know Planck's constant, we can plug everything in. Our mass of our electron, 9.1 times 10 to the minus 31 kilograms. Plug all the numbers in, rearrange, get these two numbers over to the other side, delta x. Is equal to 2.9 times 10 to the minus 10 meters, which is again approximately the size of the atom. And incidentally, there are lots of types of atoms. Actually, this is bigger than most atoms, actually, as we'll see when we do our discussion for chapter 8. So, question?
Yeah, so where did the 9.1 times 10 to the negative 1 kilograms come from?
Oh, where did this number come from? It is the mass And since we're talking about an electron, it's the mass of an electron. Yeah, I kind of put separate parentheses here for these two, but they're in the same parentheses there, which just means they're multiplied. Question, Stephen?
Could you treat that as essentially a constant? Because that's always going to be the same?
Treat this whole thing as a constant?
Yeah.
You could.
Okay.
Yeah.
It's always going to be the same.
It is. Yeah, and I don't know why we didn't just combine them. I mean, I guess because we already have Planck's constant on the list and we're familiar with pi. It'll turn out that this equation is given. Whenever I see a 4 pi, I think somebody did an integral somewhere over all space. And I bet that's what happened there, but that's not for this class. Yeah. Okay. So what we're going to do is very shortly, and in fact in today's lecture, we will not talk about the position of an electron specifically. We will talk about electrons being in places and their probabilities. Okay? That's the net result we're going to get out of this, is that due to the uncertainty in position and or velocity, we will only speak of probabilities of finding the electron. In the atom. Okay, and we're going to these things called orbitals, but orbitals will exist as volumes of space in which we have a 90% probability of finding the electron. And that's how we're defining it. So we will speak of probabilities, not of exact locations. And actually, the most exact thing you can talk about is actually the energy of an electron. And we'll talk about energies of electrons, but the positions will be in volumes of space. And so now we come back to this. For electrons, the uncertainty in its position and or velocity prevent exact knowledge of its future position. And we had the previous slide where we had an interference pattern. Now from the video last time, there was a giant eye, and when the eye determined which slit the electron went through, the interference pattern collapsed. Physically speaking, you cannot put an eye, like you can't go just like that and observe the electron, but you can use a laser. So the laser determines which slit the electron goes through. And collapses the probability field, the probability fields. That created the interference pattern. Determines which slit the electron goes through, collapses the probability fields that created the interference pattern. Meaning that with no laser, the electron goes 50% probability through one slit, 50% probability through the other slit, and you do observe an interference pattern. Once you observe the electron going through one of the slits, it can't go through both of them, and you get an interference pattern. Brenna?
Does that just mean that the first one is like
Does that mean that the first one is a trick of the light? The short answer is no. And let's see. So what we've just done with reference to right here is if we say the electron's over here, we shoot it at the screen and we observe just the screen, and we have no knowledge of its position, then the probability fields can interfere with each other and create the interference pattern. So, like in a literal way, it's the probability. Half of the probability goes through each slit. The probabilities interfere constructively and destructively to create the interference pattern. But then if we observe which slit, then it can only, there's still a little bit of uncertainty, but it's within just the one slit. And that's sort of related to what happens here. You see it spread a little bit. But there's, like, to get an interference pattern, you have to have electrons going through, or in this case, probabilities of electrons going through both slits at the same time. So the short answer is no, it's not a trick. It is science. It's just what might be called weird science. It's like when things get small, things get weird.
Because it's like if a tree falls in a forest and no one's around to hear it, does make a sound, and obviously the answer is still makes a sound, except with the electrons, the answer is that it doesn't.
Sort of.
So it's kind of weird to wrap your head around, but okay.
The classic example is something called Schrodinger's cat. Are you familiar with Schrodinger's cat? Is Schrodinger's cat dead or alive? Well, the short answer is you don't know, and what quantum mechanics says the cat is dead and alive. Because the cat exists as two distinct probabilities. And you have to say, it's a thought experiment. No cats were actually hurt in the making of this experiment. I'm not a big fan of cats. I don't dislike them that much. But what you do is, inside of a box, you put a cat, and then you put a radioactive source. There's my cat, by the way. You put a radioactive source, and the radioactive source has a half-life of, say, 10 minutes. Which means after 10 minutes, there's exactly a 50% chance that it will have decayed and killed the cat. And I think there's a poison in it. And the question is, after 10 minutes, is the cat dead or alive? And according to quantum mechanics, until you observe the cat, until you collapse the probability field, the cat is both dead and alive. Because you don't know, you have not observed it. And when you observe something, you collapse the probability field. It's weird. Now, what do we have to know? Right? Levels of understanding. First level of understanding is that if you have an electron source and no laser here, nothing to observe the electrons, there will be an interference pattern here. And you also have to know that it is the 50% probability of it going through one slit and the 50% probability of it going through another slit that interfere with each other. And this is not purely an academic exercise. Later in the semester, when we talk about bonding, we will have electron probabilities interfering to create orbitals that are associated with bonds. Okay? And we will have them constructively interfere, and we will have them destructively interfere. Probabilities. So. Anyway, and the take-home message is here, right here. We will only speak of probabilities of finding the electron in certain places. Anyway, if that's not weird enough, and actually I think the weirdness largely ends there for a few slides. Now let's get back to some equations. This is an equation, Schrodinger's equation, that is a linear algebra equation. There's no linear algebra prereq for this class, so we won't be solving this equation. All we have to know is that the solutions to the Schrodinger's equation are what give us the quantum numbers. And quantum numbers are going to allow us to differentiate orbitals and sublevels and principal energy levels in the atom. And that's all I think I want to say there. And I guess the one other thing we'll say, I'll save that. Okay, so all we know so far, quantum mechanics. I guess I can say one other thing. Quantum just means is related to quantized, and so we will find quantized positions of the electron in the atom. Quantized orbitals too. All right, so the principal quantum number, that's n, that describes the main energy level or shell that an electron occupies. The principal energy levels are very similar to the Bohr energy levels, and they go essentially like this. If that's my nucleus, this is n equals 1, n equals 2, n equals 3. And I will tell you this, we're learning a couple things. We've already talked about how as you go from n equals 1 to n equals 2 to n equals 3 to n equals 4, that the energy levels get closer and closer together. That is true. However, the spacing of the actual levels themselves, they actually get larger by the square of the number. So actually n equals 2 is 4 times as big as n equals 1. N equals 3 is 9 times as big as n equals 1. Anyway, there's n equals 4. It's 16 times as big. And so even as the energies get closer and closer together, the spacing of them gets farther and farther. And we'll see that there's actually more to say, but that is true. Good. Another thing I'll say about this is that and the principal energy levels, those are going to be the 1, 2, 3, 4, 5, 6. Like when we do electron configurations, the 1 in 1s2, that is the principal energy level. And n goes from 1 to infinity. And we've seen an example of that. There is no limit to n. Only some of the values of n have electrons in them. But in practice and in theory, there is no limit to n. The angular momentum quantum number, that's L, that's not a 1, that should be lowercase letter L. Describes the shape of each orbital. Each value of L has a specific shape. The magnetic quantum number, m sub L, designates the orientation of the orbital within the sublevel. Now the values of L, L goes from 0 to n minus 1. And m sub L goes from minus L to plus L. And we will demonstrate all this, but these are the rules. These are how the solutions to the Schrodinger's equation go. The first principal energy level, n equals 1. L goes from 0 to n minus 1, 1 minus 1, 0. M sub L goes from minus 0 to plus 0. This is not a math class. Minus 0 and plus 0 are not different things. They're both 0. And now let me say a few words about the meaning of these. N equals 1, that's the first principal energy level. It has one sublevel called the S sublevel. And M sub L equals 0. Well, the number of values for M sub L is the number of orbitals. If there's one value, there's one orbital in this sublevel. The S sublevel has one orbital. Because there's one value of M sub L.
Sorry, it has one orbital or one suborbital?
So, in n equals 1, there's only one value of L, which means there's one sublevel.
Okay.
Yeah, no, there's. One value there, one sublevel, one value here, one orbital.
I thought I heard you say otherwise.
And this sublevel, when we do electron configurations, will just be called the 1s sublevel. And let's move on to 2. Well, I still have this picture up here. Part of the answer why, if the question is in 1s, why is there not what's called a 1p? Are you familiar with the 2p sublevel in electron configurations? How many people? Because the electron configurations, actually, when we get to those, most people, especially those who had Chem 300, are like, whew, I recognize this, we're in good shape. This is all the underlying parts to that. But in n equals 1, there's simply not that much room. In n equals 2, there's a bunch more room. We will fit p sublevels in there, but not d's. In n equals 3, there's even more room, so there's room for d sublevels. And that's at least one explanation why there's no 1p sublevel. All right, so now n equals 2. I think that's our next slide. There we go. For n equals 2, L goes from 0 to n minus 1. 2 minus 1 is 1. I will say, the math for a little bit is not too bad. 2 minus 1. Sorry, my L's, I lost our script value. For L0, M sub L equals 0. This is the 2s sublevel. And whenever L equals 0, it is always a S sublevel. L equals 0, this is 1s. L equals 0, this is 2s. And the 2s sublevel has one orbital. one value, one orbital. Now, for L equals 1, this is going to be the p sublevel. And in fact, it's the 2p sublevel. 2 is because it's the second principal energy level. P is what goes with L equals 1. Perhaps you already know this. But based on the fact that there are 3 values for M sub L, how many orbitals are there in a p sublevel? 3 orbitals. Now, for whatever reason, we don't talk about how many electrons fit in each sublevel really until chapter 8. How many electrons fit in each orbital? Do you know how many electrons fit in each orbital? 2. So we'll talk about electrons, but we're talking in probably next lecture, but we're talking about orbitals now. Now let me come back and I'll do this. Let's just draw a 2s sublevel. And all of the s sublevels are spheres. For the 2p sublevel, there are 3 different orbitals. Remember, the value of L and L equals 1 tells you the kind of the shape. Here's one of the 2p orbitals. I'm going to draw it along the x-axis, and I'm going to call it 2p sub x. The second one is going to be the same shape along the y-axis. I don't know whether you've noticed this or not, but when I draw these circles, this sort of dumbbell shape overall, I am not touching the nucleus, because these orbitals do not touch the nucleus. Even when I draw them touching. This is 2py, 2p sub. And over here we've got y-axis, we've got x-axis. This is 2p sub z. The z-axis comes out of the board at you. And goes back into the board. I will attempt to draw this as if it's coming out of the board at you. That is my attempt to draw it coming out of the board and going back into the board. I'm drawing this line thicker because as it gets closer to you, as things get closer to you, they get bigger and perhaps louder. And as they get farther away, they get dashed. And so what I mean by the shape is determined by the value of L. L equals 0, those are spheres. L equals 1, those are dumbbell shapes. This is one orbital. That one orbital has 2 pieces. The electron can be here, the electron can be there, the electron cannot be in between. The space in between is called a node. A node is a surface at which there is a 0 electron density? A surface on which there is 0 electron density? What does that mean? That means that the electron cannot be there. The electron can be here, or the electrons in the sublevel. The electrons can be here. They cannot be in between. There's a node here as well. And for 2pz, the node is the xy plane. And that's why they're called planar nodes, because they take the shape of a plane. That's what the mean by the surface. Good. Questions? Okay. Yeah, Amelia.
How do you know how many nodes there are?
How do you know how many nodes there are? So that's a great question. So the first thing I will tell you is that on your exams there will be 0 questions about how many nodes there are. Okay? What you do have to know is that if I say, here's a p orbital, can you point out at least one node? You would say it's this surface. And they're relatively easy to see, I think, in general, because they're the space where there's no part of the orbital. Okay? The other thing we will see is that as you go from S to P to D to F, you get more nodes. And as you go, and we'll show this too, from 1 to 2 to 3 to 4, you also get more nodes. Okay? So basically, as the shapes of the orbitals get more complicated and bigger, there are more nodes. Is that fair enough? Is that enough? Yeah. Yeah, I think for me the interesting thing is that the electron in the 2px orbital can be here, it can be here, but it cannot be in between. And that's because these shapes are going to turn out to be probability fields. And we will say that there is a 90% probability that the electron is in these spaces. And then when it goes from one side to another, it does what's called tunneling. Tunneling is when an electron goes from one place it's allowed to another place that it's allowed without ever having been in between. That is not something we will talk too much about, but that is how it gets from one place to another. Anyway, so things are getting weird. Any other questions? Yeah, Jeff.
How do you tell if it's 2s or 2p sublevel?
Say that again?
How do you identify if it's a 2s sublevel or 2p sublevel?
Oh, good question. How do you identify 2s or 2p? So each s sublevel is spherical. So the 2s will be this one. These will be part of the 2p sub. Like if you put all 3 of these together, you get the entire 2p sublevel. And what we'll do, I think, in a couple more slides, is I'll start to draw 2s and 2p so you can see how they overlap.
So you mean we identify s from p by looking at the shape?
Shape, yes. Yeah, and it's still up here, so I'll reference it. The angular momentum quantum number L specifies shape. And that's what I mean. Here, L equals 0, that is going to lead to a spherical shape. Here, L equals 1, that's the dumbbell shape.
So you know it's s or p by looking at L?
You know if it's S or P by looking at the value of L. That's right. Any other questions? For the third principal energy level, remember, L goes from 0 to n minus 1. That means that there's going to be an L equals 0, an L equals 1, and an L equals 2. Here we are with 3s, here we are with 3p, and here we are with what's called 3d. 3d has 5 orbitals, they're pictured here. I will not ask you to draw d orbitals, I will only ask you to recognize them. You'll note that an s orbital has a sphere and 1 part. A p orbital has 2 parts, and a d orbital, well, most of them have 4 parts. One of them has 2 parts and a donut. And, but what I would suggest to you is that having 3 parts that are slightly more complex in shape is roughly equivalent to the complexity of the 4 parts here. And what we're starting to see as you go from S to P to D is that you are getting these more complicated shapes for stuffing more electrons into the same shape. That's what these orbitals amount to. Let me show you the Fs, and I'll actually do the Fs here. For n equals 4, there's 4s, 4p, 4d, and 4. And these shapes have 8 pieces. Or an equivalent level of complexity. You can see that you're cutting them up into smaller pieces. There are more nodes. And in general, the shapes are getting more complicated. Again, you should recognize an F orbital, but I won't ask you to draw it. All right. Well, now we've got all the orbitals that we need. Let's start drawing some overlap. The relationship between 1s, 2s, and 3s. The picture I'm about to draw for you will always have the nucleus at the center. Then they're just a series of concentric circles. Or spheres, I'm drawing circles to represent them. Now I'll do the same thing for 2s and 2p. And the thing that I want you to remember is that 2s and 2p end at approximately the same distance from the nucleus. So if that's 2s, then that's 2p, or one of the 2p orbitals. I'm going to call this, since this is the x-axis, 2px. So the take-home message here is that 2s and 2p sublevels end approximately the same distance from the nucleus. And 2p orbitals are more complicated shapes for stuffing more electrons into the same volume. Two p orbital shapes are more complicated shapes for stuffing more electrons into the same n equals 2 volume. And what we're starting to see, more complicated shapes for stuffing. It's a highly scientific word there. So atoms and electrons, right? Electrons and protons. All of the electrons are attracted to the nucleus. So they want to be as close to the nucleus as possible. However, they're repelled by the other electrons. So in n equals 1, it's so close to the nucleus that you can only fit 2 electrons. But in n equals 2, you can fit 2 of the electrons, basically in a spherical shape. And then it's big enough that you can stuff 2 more here, and 2 more here, and 2 more here as the next lowest energy places. And I'm not asking, we're not proving this, but this is how it works. When you make the sphere bigger, you can get even more complicated d places for the electrons to be. Because the electrons are trying to stuff as close as possible while still being repelled by the other electrons. So that's the picture. And that's how I would like you to draw it on your quantum mechanics discussion sheet, if I ask you to do it on the homework and if I ask you to do it on the exam. And if I ask you to do n equals 3, 3s, 3p, 3d, they all fit, they all end at the same radius, the same distance from the nucleus. Now, one last bit of information on this slide. P and d orbitals have lobes with different phases. Phases, if you remember, well, it says, if we go back to the fact that the electron is a wave, the wave has both higher and lower parts, which we can consider positive and negative. And it doesn't mean positive is, it just means positive is different than negative. If I draw the 2px orbital, what I'm trying to say is there's a positive part and a negative part, similar to how a wave has a positive and negative part. And it doesn't matter which one you call positive and negative, you're just trying to differentiate these, just like you're trying to differentiate these. Because if you look at the wave like this, then the negative part's on the top, and the positive part's on the bottom. What we're going to use these for is when waves interact, they can be constructive and destructive interference. And in chapter 10, when orbitals interact, there can be constructive and destructive interference based upon the phases that occur.
Based on what?
Based on the phases. What we will see is that when a positive touches a positive, there's constructive interference. And when a positive touches a negative, there will be destructive interference. Anyway, we're a ways away from that, but we're building up our picture based on these electrons and the orbitals. Okay. So those are all the orbitals. That's how they relate. We haven't done electron configurations, but you can see, hopefully, the relationship. Now let's come back to what is an orbital. And the way that we're going to do that is we're going to talk about how to get from psi to orbitals. Psi is a function that is a solution to the Schrodinger equation. It's called a wave function. Psi squared is the probability density. So this picture right here shows psi squared. And what this picture means, see how there's more dots closer to the nucleus? That means that there's a higher probability of finding the electron closer to the nucleus. So more dots near nucleus equals higher probability of finding electron near nucleus. And this is the picture of the dots, and this is the graph of the dots. And see how probability density increases as you get closer to the nucleus? That's saying there's a higher probability of finding the electron closer to the nucleus. Okay, so these are a pictorial and a graphical representation of the same thing. Okay? And good. Now, if your question is, what the hell are we doing right now? I'll ask you to hang in there for a minute, because we are going somewhere. Okay. The radial distribution function represents the total probability of a certain distance from the nucleus. It multiplies psi squared, which we've got right here, times the volume at a given distance from the r from the nucleus. Now, as radius decreases, what happens to volume? Do you know the equation for the volume of a sphere? It goes like this. What's that? 4/3 pi r cubed for the volume. 4 pi r squared, I think, for surface area. But what happens? So now my question is, as radius approaches 0, what happens to volume? The answer is it goes to 0, right? If I say, what's the volume of a circle with radius 0, you would say 0, right? And that part is, okay, well, all right, so now let's come back to this for a minute. This is the density of electron, of probability. And if we multiply the density times the volume, you get the actual probability. So if this is probability per volume, and I multiply it times volume, I get probability. And so this is probability. Of finding the electron at a certain radius from the nucleus. And it's called the total radial probability because it says, okay, I'm at the nucleus, go a certain radius out, and then add up the probability at that distance in a 2 pi radius circumference. So that's what total radial probability is. But we're just going to call it the probability. Now, as you get closer to the nucleus, your probability per volume gets bigger. As you get closer to the nucleus, your volume gets smaller. So those two things are in opposites. That's what leads to this maximum. And this maximum, and this is the graph we care about, by the way. So those of you who stopped paying attention a couple minutes ago, not that anybody did that, but if you did, now it's time to pay attention. This is the graph we care about. Does this graph look vaguely like anything we've seen before? What does it look like? Boltzmann. Boltzmann distributions. Boltzmann distributions, I mean, it's a little squished, but a Boltzmann distribution looked like this, right? And this looks pretty similar. Well, it's a little squished, and the reason it's a little squished is so that we can put other bigger orbitals on it, it turns out. But now let's talk about this. This is probability of finding an electron at a certain radius from the nucleus. There is a maximum at 52.9 picometers. That is, picometer is 1,000th of a nanometer, so move the decimal place over 3 places to get nanometers. And we know from our Boltzmann distribution talks that the average place of finding the electron is probably somewhere right around there, because all the same statistics apply, because this is dragged out to the end there. Anyway, the average is right there. And here's the big payoff. Now it's time to define an orbital. Orbital. Is defined as the volume of space in which there is 90% probability of finding the electron. The volume of space in which there is a 90% probability of finding the electron. This gets boxed because boxed things mean memorize them. It gets little stars because it's even more important. If this were Yelp, it would have 5 stars. Are there 5 stars on Yelp? I don't know, but now, or Travelocity. What's the TripAdvisor? Anyway, memorize this. Now, this picture and the area under this curve is 100% of the probability. If we want to find 90% of the probability, we can actually cut off the top 10%. And in fact, that's what you do for homework 7, problem number 21, or problem number 11. Sorry, it used to be problem number 21. And we will actually have you print these out, cut them out, weigh them, because just like for Boltzmann, if you weigh it, you get the total mass, which is equal to 1 probability. And then we will cut off 10%. And that will be the radius of the orbital. Any questions? This is a rhetorical question. Why not 100%? Don't answer that. I'll answer it. Do you see this here? The equation is actually exponential, which means this is getting closer and closer to the x-axis, and closer to the x-axis. And if you know anything about exponentials, you know that actually they never get to the x-axis. It just gets closer and closer. And so if you wanted to draw an orbital that included 100% of the probability, the orbital goes to infinity. And that's not a useful thing to do. So usefully, they decided on 90%. So 90% of the area is right here. 10% of the area is right there. Because it's impossible to get 100% before infinity. The other reason they chose 90% is because that's how atoms act. They act as if they're the size of 90%, plus or minus. What does it mean to be the size of an atom? Right? What is the size or the radius of an atom when all you have is a nucleus and an electron circling that nucleus that we can't even locate with any probability? We know it's there, but where is it specifically? I don't know. It's in these shapes somewhere, but beyond that, we can't say. There is a 90% probability of finding the electron in a 1s orbital in, well, I guess it's right there too, in that shape. If I draw the 1s orbital, 90% chance it's in that shape. 10% that it's out here. Exponentially decaying as you get farther. Okay. Now, a couple other notes. The 2s and 3s orbitals, I said, as you go from 1 to 2 to 3, you get nodes. As you go from s to p to d, you get nodes. We've seen those nodes. Now let's talk here. So, as you go to 2s and 3s, you actually have spherical nodes. Or in this case, since there's one aspherical node, and what we have to remember, so this node, still the same definition. A node is a surface. In this case, it's a surface of a sphere. That sphere is where the electron cannot go. 0 electron density. Here we have a spherical node. If you remember, what we said is we're trying to pack as many electrons as close to that nucleus as possible, but electrons repel each other. This node in 2s, notice how big it is, by the way. We said it's like 4 times as big. It's big. Is approximately where the 1s electrons are. Electrons repel each other. Why not put the 2s electrons mostly where the 1s electrons aren't? And it's a little more complicated than that. What I'm going to write right here is a spherical node approximately where the 1s electrons are most likely to be. A spherical node approximately where the 1s electrons are most likely to be. And in 3s, there's 2 nodes. One where the 1s electrons are, another where the 2s electrons are. That way the electrons are as far apart as possible, even though they're in the same volume of space. Two spherical nodes where the 1s and 2s electrons are. that's the idea. The whole idea is, where can you put the electrons so they're as close as possible to the nucleus, because that's what they're attracted to, and yet as far apart from each other, even though you're stuffing them into the same volume. Electrons always want to go to the lowest energy place, and this is telling us where those lowest energy places are. It's pretty cool. Doesn't make total sense to me either. It's a certain level of acceptance by me. And so I expect a certain, I don't expect a certain level of acceptance. That doesn't sound good. But perhaps you encounter a certain level of acceptance too. That's where we'll end for the day. We have a little bit of Chapter 7 left. Homework 7. Homework 7 is due next Wednesday. Yes? Let me think for a second. Yeah. Okay. Here's your note. Homework 7. Don't do number 11, short answer. That's the extra 10-point assignment until I tell you. It will not be due next Wednesday. Everything else for homework 7 will be due. I want to put that off until we have time to do it right. I hope that's okay. Okay, that's the end of today.